related rate. We'll continue and we'll take the next example. Remember, related rates, we have probably two different variables, at least two different variables, and we know the rate of one variable. We want to use this knowledge and some relations between the variables to come up with the rate of another variable. So here comes the second example. A classic example, you find it in every textbook. It goes like this: a 10-foot ladder rests against a vertical wall. Okay, as it happens often, if you don't have good friction, the bottom of the ladder starts sliding. And this is the case. The bottom of the ladder slides. See? And it slides, of course, away from the wall. At a rate of 1 foot per second. And you can guess what happened. As the bottom of the ladder slides away horizontally, then the top, with whatever the poor person standing on top, going to slide down. And the question is how fast the top of the ladder so how fast is the top of the ladder sliding down? When its bottom is 6 feet away from the wall. So this is a typical related rate problem. It's very wordy, and the solution involves strategy, but I would say the first thing to do is visualize the problem. The old cliche that a picture worth 1,000 words very much applies here. So let's visualize the problem. We do have a wall, and we do have a floor, like so. So here's the vertical wall and a vertical floor and a horizontal floor. And the ladder is rest against the wall, like so. So here's the ladder, and let's kind of put some steps here. Let's express my artistic skills. And so we're going to define the horizontal axis as x, of course, and the vertical y. And on this little schematic, we'll try to show what we know. Okay, so we know the length of the ladder. The ladder is 10 feet long. We also know that the bottom is moving away from the wall in this direction, and if this direction is x, then the rate will be dx dt, and in this case it would be 1 foot per second. The other thing that we are told that at the time where the distance of the bottom of the ladder is 6 feet away from the wall, so we call it x equals 6. We want to find out at what rate the top of the ladder is sliding down. So sliding down, it will be the rate will be dy dt, and this is pretty much what we want to find. So by drawing this kind of, the story becomes clearer, and the other strategy is to actually write down what is given and write down what is it that we need to find. So let's see, what's given to us, the following, that L equals 10 foot. So there is some measure of redundancy here, but it's good to list. The other part is we know that dx dt when x equals 6 equals 1 foot per second. Okay, so this is the data. What we need to find is dy dt. And in the solution, we need to find the relationship between x and y, I guess, because those are the two variables involved. And any suggestion how we can tie x and y and L together? Speak, guys. Pythagorean theorem, exactly. So we're going to apply the Pythagorean theorem and say that x squared plus y squared equal L squared. Two things. First of all, we want to know what is the value of y when x equals 6, but also we want to solve for dy dt. Before I continue on, can you tell me what do you know at this point about dy dt? If you want to check your solution for a common sense answer, what will be the first thing that you can anticipate dy dt to be? For instance, will it be positive? Will it be negative? It will be negative because the bottom is coming down. So if you end up having a positive solution, you know that you didn't have the right solution. All right? Good. So at this point, I'll go ahead and differentiate everything. And again, the power of implicit differentiation. And L is, of course, L squared is 100. And after doing so, you end up by the chain rule, the d dt of x squared will be d dx times dx dt. And d dx of x squared is 2x, and then dx dt. Same with y. D dt of y squared will be dy squared dy, which is 2y, times dy dt. And of course, the derivative of 100 is 0. Solving this, you have reduced by x, and you have y dy dt equals negative x dx dt, right? And therefore, dy dt, you can write it as negative x over y dx dt. Of the three quantities to the right, x, y, and dx dt, we know two. We know x equals 6, we know dx dt equals 1, and we need to find y at this point. So once again, we'll go back to the Pythagorean theorem, and we're going to find the value of y. So y is the square root of 100 minus x squared. And since x squared is 36, we are talking about, we end up having 8 feet. Notice that we take only the positive root as y equals -8 has no physical meaning. And now we're pretty much done. At this point, dy dt, when x equals 6 and y equals 8, is negative, x is 6, y is 8, dx dt is 1, or negative 3/4 feet per minute. Per second. Okay, so that's it, folks. I'll let you drive.